All right, I want to go through some of the homework questions that you had from the other day and see if we can kind of help out on this. So the first one that a lot of you marked was problem number 43. There was 3 parts to 43, but mainly part A was the one that you were asking about. And this one we wanted to find the area for. So if we look at this one here, and I try to partition it up, probably the best thing to start with might be to make this vertical line here. Because if I do that, I know that the entire thing is 9, but since this part is 5, that tells me this part is 4. All right, so I can label that part. Why that's important. If I were now to partition this into a right triangle, I know that that dotted line I made is also 4. So even though it doesn't necessarily look like it, we've got 4, 4, 4. This side would also have to be 4, which means really I'm dealing with a square down here. So area-wise, I know that's going to be 16. In order to find the other 2 areas, we had to find a little bit more information. The nice thing, though, is that triangle that we just created, the right triangle, has a hypotenuse that's 4 square roots of 2, and now I know one of the legs is equal to 4. So if I want to do the long way, I could do Pythagorean theorem and find that third side. Or hopefully we notice that, okay, the hypotenuse is 4 square roots of 2. One of the legs is 4, which means this is really a 45, 45, 90 triangle, which means this side now is also 4. So if I look at the entire height of that rectangle, I've got 4 and 4, or I've got 8. So I can take 8 times 5 to get this area. That triangle we just looked at, now it's 4 times 4, so 16, but we cut it in half because it's a triangle. And I've got the 3 pieces I need for my area. So when I put all those together, I'll get my area. So what do we end up with there? 64. And I don't remember if they put units on that or not. They did not, so we just say square units. Okay, so recognizing that 45, 45, 90 would be helpful now. On number 44, you had 4 different problems here, but each one wanted to figure out what the number of sides would be in a regular polygon when they gave you each interior angle. The one that was marked the most was the second one, the one where they gave you 156 degrees. Well, let's kind of think through what we would need to know to find the number of sides. Well, if we knew the interior angle sum, which would be n minus 2 times 180, I could take that interior angle sum and I could divide it by how many sides we have. And that should give me what each interior angle would be. Well, for number 2, that's 156. So essentially, I'm trying to solve this equation. So how can I solve this equation? Well, I probably want to get rid of the fraction, so I'm going to multiply both sides by n. I'm also going to go ahead and distribute that 180. So I have 180n now minus 360 is equal to the 156n. And so now I can solve it in a couple steps. If I subtract the 180 from that other side, I get negative 24. And I'm going to take 360 divided by that 24, or negative 360 divided by negative 24. And I find out that it had 15 sides. And I could have done the same thing with all those others. Again, kind of using that formula as a way to help us out. So working backwards, especially on that type of problem, sometimes gets a little bit tricky. All right, 45, they wanted to know which of these were going to be similar, which in some ways is a little bit of a trick question because anytime I have a circle and I'm comparing it to another circle, they're going to be similar to each other because all circles are similar. why would that be the case? Well, remember, similar figures have the same shape, which obviously every circle is the same. And then they also have a zoom factor or a scale factor of some sort. And the only thing I really have that's a measurement in a circle would be what the radius is. It really is what dictates the size. So if I only have one value and then I'm comparing it to another circle, well, there's only one zoom factor or only one linear scale factor. For instance, if I went from this circle to this one, my linear scale factor was 3. If I went from a half to 3, that means my scale factor was 6, and so on. So just a reminder, all circles are going to be similar figures to one another. And then the last one that you had marked, number 46. So number 46, they had a scale drawing of this dollhouse. And they said that the actual one was 5 times as big. So 5 times the measurements for the sides at least. So well, part of it, they wanted to basically come up with, well, what are you starting with? If you looked at the diagram, what was the area? What was the perimeter? All right, well, we basically had everything we needed on here as far as labels, other than a couple of the sides. So as we go across, we know it's 20 total. I've got the 8, I've got the 4, so we're up to 12. So that means this had to have been 8. From top to bottom, this was a little bit trickier, but from top to bottom, we had 12. They said, though, from here to here was 9. From here to here was 3 because of this value here. So that means that I would be left with, well, actually, I didn't even need that extra piece of information, but that leaves me with 3 there. So when I put it together, this whole piece would have been 6. All right, so from there, you could find your area, depending on how you wanted to attack it. And I got a lot of markings here, so. Yeah. You could probably break it into different rectangles. If I were doing it, maybe I'd break it into these rectangles. So we have a 12 by 8, so 96. We've got rectangle in the middle, so that's going to be what, 4 by 6, so 24. And lastly, I got a 9 by 8, so 72. So I put all those values together, the 96, the 24, the 72, and so I get here at 192. Perimeter would just go around the edge, add all those up. So hopefully that part wasn't too bad, but you should have found out the perimeter was going to be 7. All right. Well, part B, they said, we'll draw a similar figure. So we know the shape's going to be the same. They said they wanted it 5 times as big. So you're going to label those new measurements on there. The next question, though, talks about what's the perimeter and the area for that. So if we look at all those different pieces that we had on there, you could go through the steps of finding what the new perimeter was and the new area was by just using the new figures if you wanted to. What we're going to work on, and hopefully now that we've done some more examples, is maybe I don't have to do that extra work. I can maybe look at something else to help us out. So when you get to part C and part D, it said, well, what's the ratio of the perimeters, first of all? Well, the ratio of the perimeters should match what the ratio or the linear scale factor was originally. And they said it was 5 times as big. So the ratio of the perimeters of the two figures should be 5 to 1. Or in other words, the ratio of the perimeter should be 5 times as big. So that means when you did the perimeter of your new figure, it should have been 70 times 5, or 350 centimeters. Where you show the areas. Well, we've done a few examples now where we talked about, well, the ratio of the areas is really the scale factor squared. Or in other words, it should have been 25 to 1, or 25 times as big. So I'm going to take that 192 now, and I'm going to multiply it by 25. So once we do that, we end up with our new area. So our new area, once we take it times 25, is 4,800 square centimeters. So how does the ratio of the areas seem to be related to the zoom factor? Well, again, it's the zoom factor or the linear scale factor squared. So those are the ones that you guys marked the most. Hopefully that helps out a little bit. If you have additional questions, let me know, and I can also go through those as well.